Welcome back, Nature in Code. We're in chapter 6, and we just finished our observation of directional selection. Directional selection is when the heterozygote has intermediary fitness of the two homozygotes, and this is the outcome of this process, which is that independent of the value of P, so independent of the current frequency of the A1 allele, delta P is going to be positive, which means that P will increase, the frequency will increase over time, and then as a consequence of that, the allele will simply go to fixation, and that is the consequence of directional selection. Now, we've seen previously on the slides that there are two other types of selection, so we just looked at directional selection. Now let's move on to the next type, balancing selection. So balancing selection occurs when the heterozygous coefficient the heterozygous effect is negative, which means that you get this fitness peak here. So the fitness of the heterozygote is the highest fitness. It's higher than both the fitnesses of the homozygotes. So what happens in this case? Well, we've already written most of the code to understand this. So let's go to our code. So this is my file, delta P versus P. If you don't have that open, be sure to open it. And the only thing I need to change here now is the value of H, because the value of H defines the type of selection you have. And as I said, balancing selection requires negative H values, so I'm just going to set this to minus 0.5. So I'm going to save this, and I'm going to go over here and reload the delta P versus P tab. And if I do this, I get this figure. And this is now quite interesting. So still in most of this space, the value of delta P is positive. However, in some of the space here, when P is quite large, then it is actually negative. So what does that mean? Well, let's think about this again in the same way as we did before. You know, imagine you're somewhere here at a low value of P. While delta P is positive, which means that in the future, in the next generation, you're going to move a little bit to the right because P is going to increase. And because you're consistently here in a space where delta P is positive, you're consistently moving to the right at all times. And then this will go a little faster here because delta P is quite large. And then this will slow down a little bit and slow down, slow down, slow down, until eventually you hit this point where delta P is 0, which means P is not going to change anymore. So it's reached an equilibrium. Okay, what happens over here? Well, the exact opposite happens. You're at a quite high value. However, your delta P is negative, which means you're going to move to the left a little bit. Move to the left, move to the left, move to the left until you hit this point here where delta P is 0 and P is not going to change. So again, if you get pushed out over here, you're going to move slowly back to this equilibrium point. If you get pushed out a bit to the right, you're going to move slowly back to the left to the equilibrium point. So what seems to be happening, the prediction here is that independent of where you start, you are going to end up at this value of P that is 0.75, it seems, but it is not 1 or 0. It is some intermediary value. So let's go ahead and change our P versus time code to demonstrate that this is true. Now, again, we could, of course, just go in and change the H value, but I want to change the code a little bit more so that I don't have to start at a particular P value, but that I can start at many different P values at the same time and have many simulations and then see what happens. So let's go ahead and do that. So I'm going to open the file here, P versus time. And let me just close this tab here. So the first thing I have to do, of course, is to set the H value here to minus 0.5 as well. And then what I have to do is change this here a little bit. So the first thing I would like to do is, not to call this P, but rather initial p, because I'm going to set up an array that holds a lot of different p-values that the simulations will begin with. And the first one just happens to be 0.01. And so I'm going to set up here this array I'm going to call p-values that I'm going to initialize as an empty array. And this will hold the initial p-values for all the simulations. And so that's fine here, the data array, which will be two-dimensional in this case, and then generations, that's fine too. So the first thing I want to do is I want to fill up this p-values array. So I'm going to use a new type of loop here that we haven't encountered before. It's actually very simple. It's the while loop. So I'm going to say here while initial p smaller than 1. So this is this value here. So a very simple condition. While this condition is true, do the following. Push this initial p into p-values. Okay, p-values push, oops, initial p. And then be sure to increment this value by, say, 0.01. So this is the while loop. It's like the do while loop, except that the do while loop had a do before the while, and so that do guaranteed that you would execute the code at least once, and then you would keep doing it while the condition was true. The while loop is a little simpler. It just basically checks, is the condition true? If yes, I'm going to iterate this. I'm going to execute this as long as this condition is true. So there might be situations in a while loop where the condition is not true right from the get-go, and you would never execute this code here. And so the do while is sort of a small change from that, in the sense that it will execute at least once. That's not true for the while loop. But then on the other hand, the while loop is a little easier. Okay, so that fills up my p-values array. Now, so I would like to run this code here many times for different values of this initial p. So I'm going to just put this here. I'm going to wrap this into a function that I'm going to call run simulation. So I'm going to wrap this here, this whole thing, in the function. Okay. And then I'm going to basically pass this function a corresponding p-value from which it can start. Now, the only thing I need to take care of here is I shouldn't push these values, the p-values then that will be calculated, directly into data, because now my data will be a two-dimensional array, in the sense that it basically contains arrays that contain the values, just like we've done before in the drift simulations, where we had multiple simulations in the same graph. So I'm just going to set up an empty array here that I'm going to call results. And then I'm going to push the calculated p-values into this results array. And then at the end of the for loop, I'm going to push the results array into data. And that's what we want, right? We want the data array to contain many arrays that contain the results. And so now the only thing that I have to do is I have to make sure I actually call this function run simulation as many times as I want to, with the corresponding initial p-value that I want. So I'm going to do this with a for loop for var I equals 0. How often? Well, however many initial p-values I have, and that is exactly the length of the array p-values. And then, of course, increase I by 1. And now simply call this function run simulation and pass along the corresponding value here in p-values, so the ith value in p-values. And now if you do this, just save it and reload it, and you should see this. And this exactly demonstrates, proves that our thinking was correct, independent of where you start here with your initial allele frequency. You will go to this intermediary value, which here is at 0.75, and it is at 0.75 because if you look here at the delta P versus P figure, that's exactly where that's supposed to happen. That's exactly where delta P is 0. Okay, so this is balancing selection. Now, this is really interesting, right? If you go back to our slides, balancing selection occurs here in this space where the heterozygous effect is negative, which means that the intermediary, the heterozygote genotype has the highest fitness. And so as a consequence, the other two genotypes cannot just take over, because this guy, A1, A2, has the highest fitness, and it will maintain this genetic diversity, right? P will neither reach 0 nor 1, but it will reach an intermediary stable value and will not go away from that value. So it will maintain this balance of alleles, and this is why it's called balancing selection. And this is really interesting because this is a force now that maintains genetic variation, and that's really a really important phenomenon. Now, what is the intermediary value, or this balancing value of P, going to be? Well, we looked at the graph and we could see, okay, wherever delta P is 0, it turns out that you can actually calculate this quite easily. Where is delta P 0? And it turns out that this is at a specific point, which I'm going to call here P star. And it is simply H minus 1 divided by 2H minus 1. And now if you keep in mind the value we had for H, we had minus 0.05. So, in this case, minus 0.05 minus 1 is minus 1.5. And then 2 times minus 0.5 is minus 1, minus 1, minus 1. Minus 1 is minus 2. And so that's divided by minus 2. And so that means, minus cancel each other, and 1.5 divided by 2, of course, is exactly 0.75. Now, the other interesting aspect about this is that you don't see S in this equation, and that's quite interesting. So it doesn't matter what S is. S will only affect the dynamic of the process. So if you change, for example, S here, and let's say you double S to 0.2, and then you go back and reload this. Oops, go back here. What you can see is it just happens faster. Vice versa, if you go back to the code and you decrease it to 0.05, it still goes to the same value, it just happens slower. So S, the selection coefficient, will determine how fast this equilibrium will be reached. But where the equilibrium will be reached, the value of the equilibrium is completely determined by this heterozygous coefficient. And that's why this value is so important. So not only does it determine the type of selection you'll get, but also if it gets to an equilibrium, where that equilibrium will be. And that is balancing selection. So in the next video, we'll look at disruptive selection. I'll see you there.